So hopefully by this point with Faraday's law, you're kind of comfortable with this idea that, hey, if I take this loop and move it through this magnetic field, right? Like if I give it a velocity as it's entering that magnetic field, there's going to be current, there's going to be an EMF generated or induced by that change in flux. And that's just Faraday's law. It's really what Faraday's law is telling us. The induced EMF is equal to the number of loops times change in flux over change in time. If you have a change in flux, you get an EMF and an induced current. Now, the question becomes, well, what direction is that current going to be? That's kind of what this negative sign tells us. There's this way there actually is a way you can use right-hand rule. I read this in the textbook. You can use right-hand rule, and it's like you have to do right-hand rule, and then the negative tells you flip your thumb, and then that tells you the direction of the current. But that's stupid, and no one wants to remember that. Lenz's law gives us an easier way to think about it. So what Lenz's law tells us, this is like just the verbal definition of Lenz's law. It tells us that so I'll write it down. The induced, let's write it like this. A change in flux will create an induced EMF that will, I don't know why I just went silent. A change in flux will create an induced EMF and current that will create a B field opposing the change in flux. So we know that a moving magnetic field or a change in flux creates a current in an EMF, and we also know current creates magnetic fields. That's like the find the B field due to this long wire or whatever, right? To mu naught I over 2 pi r. That so that means whatever current is induced in this loop will create a magnetic field, and that magnetic field will try to oppose the change in flux to keep everything the same. It's a conservation of any energy idea, but I'm going to talk more about conservation of energy in a second to make that connection more clear. But the way you really go about finding the induced current, the direction of the induced EMF current, they're the same direction, right? Because EMF creates current. So the way you go about it is you got to first think about step 1, what is the change in flux? So we know as we're entering this into a B field directed into the page, there's going to be more, right now there's 0 flux, and then there's going to increase the flux as I'm entering it in. There's going to be an increase in flux into the page, right? So the second step is I have to find what is the opposite, what needs to oppose that, right? So the opposite to oppose the change in flux, well, you need less flux, right? Going into the page, right? So you gain flux going into the page. You want less flux going into the page. How do you get that? Well, you can't physically reduce the magnetic field. Like it's uniform. You can't get rid of any B field. You have to oppose it by having magnetic flux coming out of the page, right? So we need more now. Well, to the opposite is going to be flux coming out of the page, right? So the opposite is flux coming out of the page, and the third step is to determine what current will create a magnetic field that points out of the page. So you would use your right-hand rule, right? So let's use which right-hand rule? We can use the first right-hand rule. We want B field. So if I were to kind of draw this entering the and I'll use red for this. If I were to draw the loop going into the page now, like so, right? There obviously needs to be now new field lines induced that are out of the page. And that would mean my fingers are coming out of the page like so, and you can see pretty naturally my thumb is pointing up. And as it goes in this direction, all the magnetic field is coming out of the page. and I can even, there's going to be some here, 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 whatever. So in order to get magnetic field coming out of the page, my induced EMF and my induced current is going to be counterclockwise. So you have to find the current that will create the opposite, which in this case is counterclockwise. So that's how you can use Lenz's law to figure out the direction of the current. I don't know why I'm blanking. It's just how you can find the current without really having to worry about the negative sign. One way you can think about the negative sign is that like the EMF will always be opposite to the change in flux. So that's another way you can think about it, right? So if your change in flux is like positive, your EMF is negative. I don't love that explanation because it's like, well, EMF negative, what does that mean? Does that mean clockwise or counterclockwise? But really it means that like the EMF is gonna create the opposite effect on the change in flux. That's one way you can think about it. Now, what I want to talk about is really how does conservation of energy kind of come into play here? And it kind of makes sense, right? Like I'm getting flux into the page, so there's going to be probably some flux coming out of the page to offset it to keep everything the same. But to expand on that idea a little bit more, think about it like this, right? Like, let's say I give the loop a little bit of push, a little bit of initial velocity into the page, right? Or not into the page, we're going to the right or whatever, right of the page. It's gonna have some kinetic energy, and the objects in motion will stay in motion, right? So if it were to just enter the magnetic field at the same velocity, same constant velocity, it's going to have the same kinetic energy, right? Because kinetic energy is just 1/2 mv squared. But then all of a sudden it's going to get current, and that's electrical energy, right? You can use that, like if this was, you could attach a light bulb onto here, power that light bulb, you're getting electrical energy out of nowhere. So if you think about conservation of energy, you're going to expect that, okay, something has to compensate for that electrical energy. I can't have the same kinetic energy going into the page and have electrical energy. I'm getting energy out of nowhere. So what makes sense? Well, as you are entering into the magnetic field, you're going to get a decrease in kinetic energy as your electrical energy increases, right? As you get current, you're going to slow down because the energy is transforming. So how do things slow down or accelerate in general? You need a force. So if I want it to slow down, I'm going to need a force this way, right? Now, what could create that force? Well, guess what? Now there's current flowing through this thing. A current in a magnetic field creates a magnetic force, right? If you think about F equals ILB. So there's going to be a magnetic force, and it's going to have to oppose the opposite way. If it were to oppose, I don't know why I'm saying oppose. It would have to point the opposite direction of the velocity. If it went in the same, right? If it went in the same direction as the velocity, it's going to speed up. And if it speeds up, it gets more change in flux. And if it gets, right, because of the change in flux over time, like it's increasing at a greater rate, the flux, it's going to have a greater rate of change of magnetic flux. That means more induced EMF. That means more electrical energy. That would violate conservation of energy, right? It would have to be the other way so that it slows down, and then that kinetic energy can transform into electrical energy. How do you get a force going this way? Well, then you just use the right-hand rule. If you use the palm right-hand rule, I want a force going this way, and then my magnetic field points into the page, right? So if my fingers are the magnetic field, it's pointing into the page. I want to force this way. My thumb shows that, hey, the current is going to go up this, little section of wire. It's going to go counterclockwise. If Lenz's law wasn't true and it went the other way, then that means thumb this way, magnetic field into the page. I'm getting a force that way. That's going to accelerate it even more. Conservation of energy will be violated. So hopefully with forces, that kind of is. It's kind of incredible, actually, that the universe kind of knows in its own weird way that, like, the current has to be this way so that we can get a force that way. Well, the universe isn't thinking anything, but hopefully that's kind of incredible to show that like the universe just has current going this way, and that creates a force this way, and energy is still conserved. It's like conservation of energy is like ruling the entire universe. I guess it is, right? You can't create or destroy energy, so everything balances out, and you don't get energy coming out of nowhere. So thank you for watching. Hopefully this video made sense. It's a little bit rambly, just because I don't know, I'm a rambly person. But yeah, hopefully this video made sense. Thank you for watching. Have a good one. Lenz's Law.